Have you ever wondered how scientists separate and identify complex mixtures? Welcome to the intriguing world of gas chromatography, often referred to as GC. This powerful tool is a mainstay in chemistry, allowing us to unravel the mysteries of complex mixtures with remarkable precision. Imagine having a cluttered drawer filled with a variety of trinkets. Sorting them out one by one would be quite a chore, right? Well, GC does a similar job, but for molecules. It separates the components of a mixture by exploiting their different interactions with a stationary phase. Picture a microscopic racetrack where each molecule is a competitor. They race along a track with their speed and path determined by their individual characteristics. The result? A neatly sorted array of molecules ready for further examination. So buckle up as we delve into this fascinating realm and think of it as a microscopic racetrack where molecules compete based on their individual characteristics. The story of gas chromatography unfolds in the 1930s with two British scientists, Martin and Synge. Their quest to understand the complex world of fatty acids led them to an unexpected discovery. They observed how different components of a mixture separated when carried by a moving gas through a column packed with starch. This was the humble beginning, the first step on the path to what we now know as gas chromatography. However, like every great scientific breakthrough, the development of gas chromatography didn't stop there. It was further refined in the 1950s, thanks to the diligence and ingenuity of two other scientists, James and Watts. They took the foundational work of Martin and Synge and built upon it, enhancing the technique to offer even more precise and reliable results. This marked the birth of GC, later refined by James and Watts in the 1950s. The legacy of their pioneering work continues to shape our understanding of the world on a molecular level. Gas chromatography operates in a three-step process. Let's break it down to better understand how it works. First, we have the injection. Here, the sample, often a liquid, is vaporized and injected into a hot stream of carrier gas. Picture this as a puff of smoke being launched into a breezy afternoon. This carrier gas, typically helium or nitrogen, is similar to our afternoon breeze, propelling our sample down the path ahead. Our second step is the separation. The vaporized sample mixture is now traveling through a long coiled column. This column, akin to a microscopic maze, is packed with a stationary phase. Now, the stationary phase can be either liquid or solid, and it plays a pivotal role in our process. Each component in our sample mixture interacts differently with this phase. Some might linger, forming a bond with the stationary phase, while others might scurry along, barely interacting. This difference in interaction directly affects the travel time of each molecule, effectively separating our mixture as it moves through the column. Finally, we come to the detection. This is where we get our results. As the separated molecules emerge from the column, they are detected. Picture a finish line at the end of a race, where each runner is acknowledged as they cross. However, in our case, the finish line is a sophisticated detector. This detector senses the individual components and generates a signal in response. The signal, when plotted as a graph, forms what we call a chromatogram. This chromatogram is like a molecular fingerprint, revealing the identity and amount of each component in our original sample. It's through this process that we can analyze complex mixtures, separating and identifying each part, much like sorting through a drawer of trinkets. As separated molecules emerge from the column, a detector senses them and generates a signal. This signal, in essence, unveils the hidden components of our mixture, giving us a clear and precise look at what we're dealing with. Gas chromatography's versatility shines in identifying a vast array of molecules. Let's explore this fascinating versatility. One of the most widespread applications of GC is in the identification of organic compounds. This is crucial in environmental analysis, where GC is used to identify pollutants in the air we breathe, the water we drink, and even the soil that nurtures our crops. GC also has a starring role in the world of flavors and fragrances. It helps us detect and quantify the volatile compounds that give food and beverages their unique aromas and tastes. So, the next time you take a bite of your favorite dish or take a whiff of a fragrant flower, remember, there's a good chance GC was involved in perfecting that experience. In the pharmaceutical industry, GC is the unsung hero that ensures the purity and potency of medicines. It plays a crucial role in drug development and quality control, helping scientists identify any impurities that might sneak into the medication during its production. This is vital because even a tiny impurity can have serious implications for patient safety. Then there's the petroleum industry. From gasoline to lubricants, petroleum products are complex mixtures of hundreds, sometimes thousands of different hydrocarbons. GC is employed to refine and analyze these mixtures, ensuring optimal performance and safety. But GC's utility doesn't stop there. It has a significant role in medical research and diagnosis too. It's used in the analysis of biological samples such as blood or urine to identify and quantify specific compounds. For example, GC can analyze fatty acids in blood samples, providing valuable information about a person's nutrition and metabolism. It can also identify biomarkers in disease, providing crucial clues for diagnosing medical conditions. From analyzing fatty acids in blood to identifying biomarkers in disease, GC aids in medical diagnosis and research. This gives us a glimpse into the broad range of GC's applications. It's a powerful tool that helps us understand and navigate the complex chemical world around us, making our lives safer, healthier, and more enjoyable. While powerful, gas chromatography has its limitations. Just as every hero has an Achilles heel, so does our trusty technique of gas chromatography. For starters, it struggles with large non-volatile molecules or those that are heat-sensitive and decompose easily. Think of these as the heavyweights in our molecular race who either refuse to run or worse, collapse under the heat of the competition. Then there's the challenge of separating very similar molecules in complex mixtures. Imagine trying to tell apart identical twins in a crowd. It's no easy task. Lastly, the cost and expertise needed to operate GC instruments cannot be ignored. These machines are not cheap and they require a skilled operator at the helm, much like a seasoned captain steering a ship. Despite its limitations, GC's impact on various fields from food safety to medical diagnosis is undeniable. As we advance in technology, its power will continue to grow, offering even deeper insights into the molecular world around us.